We have developed a pretty full conceptual framework and quite a bit of mathematics for dealing with linear time invariant systems. And what I'd like to do in this presentation is tie together some of the different aspects of the theory that we have developed. So let's recall a few things about Laplace transform. First, the big idea behind the Laplace transform was that we could take an arbitrary signal x of t and we could break it up into a sum of everlasting exponentials. So we can write x of t is the sum of xi e to the sit, where xi are the coefficients. And given a sufficient number of exponentials, we could represent any x of t. The notion is that we would use an infinite number of exponentials, and then the summation would turn to an integration. And the Laplace transform is simply a means for finding the coefficients in this expression. So we know we can break up an arbitrary signal x of t into the sum of everlasting exponentials, and we know how to find the coefficients in that representation via the Laplace transform. But the question still is, why break it up into everlasting exponentials? I hinted at this a bit before in a previous presentation. In this presentation, we're going to go through it in more detail. I hope by the end of the presentation, the whole framework will become much clearer. Now, our first step is to recall that the zero-state response to an everlasting exponential input was an everlasting exponential output. So, we have a linear time invariant system. We put in x of t equals e to the st, and in response we get y of t is h of s times e to the st, where h of s is just some constant that's dependent upon the value of s that we've chosen for our input, and e to the st is an everlasting exponential. So the output looks just like the input, it just has a different magnitude. Now, we showed this by convolution. It was a simple matter of plugging in x of t equals e to the st into the convolution expression, and we were able to arrive at this result. So now let us suppose that instead of putting in a single everlasting exponential, we put in an input that's a sum of everlasting exponentials. X of t is x1 e to the s1t plus x2 e to the s2t plus and so on through xk e to the skt. That expression I label double star here. Now, from superposition, the output must be the sum of the outputs as if each exponential was applied alone. So, for example, if we put in the input x of t equals xi e to the sit, we know we'll get the output y of t equals h of si times xi e to the sit. Otherwise, we just took the input, which was xi e to the sit, and we multiplied it by the constant h of si. That holds for the ith exponential that we have here, and it will hold for all the exponentials in the summation. Therefore, by superposition, we know the response to the input double star above is y of t is h of s1 x1 e to the s1t plus all the way through to the last exponential h of sk xk e to the skt. So we're just finding the response to each one of the xi e to the sit by multiplying it by h of si and then summing them all together. So for this particular input, which was the sum of everlasting exponentials, we could find the output without convolution. We noted before that for a single everlasting exponential, we could find the output without convolution. We simply need to multiply by the particular transfer function. But now we find out that we can do this also for an input that's a sum of everlasting exponentials. Now, most inputs cannot be expressed as a finite sum of everlasting exponentials, but we know for our expression for the inverse Laplace transform that we can create an arbitrary input as the sum of everlasting exponentials as long as we use an infinite number of everlasting exponentials. That is, we're using an integral. So the equation we had before was x of t equals 1 over 2 pi j integral in the complex plane of x of s e to the st ds. The integration, of course, is just a summation. The x of s are just coefficients, and then we have the everlasting exponentials, e to the st, for each value of s along the convolution integral. So we can express an arbitrary input as the sum of everlasting exponentials as long as we use an infinite number of exponentials. So now that we can connect that idea for the inverse Laplace transform to what we just had on the previous page, where we showed we could find the response without convolution to a sum of everlasting exponentials, which would include a sum obtained by doing an integral. So as before, let's use superposition to find out what the output would be to this particular input, that is the integral. The response of a linear time invariant system to each part of the integral, and each part is going to be an x of s e to the st for some value of s in the complex plane. The response to that will be h of s times x of s e to the st. And now we can go ahead and do the summation of all those responses because we're using superposition. The summation of all these responses then will then be y of t equals 1 over 2 pi j summation in the complex plane h of s x of s e to the st ds, because h of s x of s e to the st is the response to each part, and then we have to sum all those together for all the different values of s that we're considering in the complex plane, and that then will be the response y of t to the input x of t. And you note that we've obtained that answer without ever having to do any convolution. Now we did have to find the coefficients x of s, which involved doing the Laplace transform of x of t, and we needed to know what h of s is from the differential equation, and then obviously to find y of t here we're going to have to do this integration of the complex plane, but nevertheless we found the response without any convolution. Now we've found the response y of t without any convolution, and of course we can relate this back to the frequency domain. We'll have y of s is the integral from minus infinity to infinity y of t e to the minus st dt, which is of course the Laplace transform. The inverse transform is y of t is 1 over 2 pi j integral in the complex plane of y of s e to the st ds, just from the definition of inverse Laplace transform. But now I want you to compare that, the definition of inverse Laplace transform, back to the answer we just found on the previous page. That was y of t equals 1 over 2 pi j integral in the complex plane h of s times x of s e to the st ds. And we obtained that result just by arguments from superposition and the argument that an everlasting exponential will have the special relationship with a linear time invariant system. And now you're comparing these two expressions for y of t, and you'll note that for these two to be equal, we must have y of s equal to h of s times x of s. So that then gives rise to this interpretation. When we write y of s is h of s times x of s, what we're talking about is how to express the coefficients of y of t's representation in terms of everlasting exponentials to the coefficients of the representation of x of t in terms of everlasting exponentials. The transfer function relates these sets of coefficients, and that's what the meaning of it is a relationship between the coefficients in the expressions for the everlasting exponential. So I hope you see how these various ideas in the time domain and the frequency domain are connected together. And the role of the everlasting exponential in tying these things together. The everlasting exponential is an eigenfunction of the linear time invariant system. Therefore, the output to an everlasting exponential is going to be a constant times the form of the everlasting exponential itself. And it's from this and the idea of superposition that's what gives the Laplace transform its essential power, because it allows us to transform to the frequency domain, find the coefficients, and then we can relate the coefficients in the frequency domain between inputs and outputs by multiplication. So now I just want to point out a remarkable fact which may not have occurred to you in our discussion about Laplace transform and eigenfunctions and so on. It is the following: that when we deal with Laplace transform, x of t is a causal signal. Okay, because we go into Laplace transform causal things when we're using unilateral Laplace transform. But e to the st is non-causal. It exists for all time. We're not talking about e to the st times u of t. We're talking about e to the st as a non-causal signal. So when we write the inverse Laplace transform, what we're saying is that we can make a causal signal out of the sum of non-causal signals, as long as we have an infinite number of them. And I think that's kind of remarkable if you think about it, that we can get all these non-causal signals to add together and be zero for all time before time zero. And then after time zero, they all add together to create something like a step, for example. So it's a remarkable thing. You can sum together an infinite number of non-causal signals and make a causal signal.
Man, this convolution integral is tough. I wish there was an easier way to do this.
Psst, Neo.
Who are you? And how do you know my name?
I am Trinity, and this is Canasius, and we know a lot about you. Have you heard of the Laplatrix?
The Laplatrix?
Yes, the Laplatrix. Do you want to know what it is?
Yes.
The Laplatrix is all around you, Neo. It's a way from transferring from the time domain to the frequency domain, and it's a method which has been hidden from you by your teachers and professors for a very long time.
Wait, you mean I can't trust my professors?
No way. Especially not that Gabriel Laufer character, having you graph all of your data in terms of time.
My God.
Come with us. Welcome to my lair, Neo. You'll see on this table I have 2 milkshakes from the cookout. On the left, my left, you have a banana praline milkshake, and on my right, your left, you'll find a cheerwine float. If you choose the cheerwine float, you'll be stuck here in the time domain, toiling endlessly, trying to find the zero-state response of a linear time invariant system. But if you choose the banana praline milkshake, I can show you the Laplatrix. The choice is yours, Neo.
Cookout. Where are we?
We're now in the frequency domain, Neo.
How did we get here?
We got here by way of a Laplace transform. We are now made up of the sum of everlasting exponentials. You're the same as you always were. You are just multiplied by e to the st and integrated to infinity.
Wait, so instead of a plot of time versus position, we're in the sum of infinite frequencies with different coefficients?
You're correct, Neo. You're learning very quickly, my son.
I didn't know this existed. So if you get the answer wrong in the frequency domain, does that mean that you get it wrong everywhere?
Yes, Neo. The body cannot live without the mind, you see. Now that I've opened your eyes to this Laplace transform, you see the great challenges that we face. The convolvers. The convolvers have been trying to convolute our minds with their convolution integrals for years. They're a mighty force.
Look, it's them. They're convolving. They're trying to get us to convolve too. So that's how you find the impulse response.
Stop, Neo. I've shown you there's an alternate method to what they're doing. Use the frequency domain.
Wait. So you're saying that I can find the zero state response without convolution?
Yes, you can.
Let's get it, Matrix T-minus now. Yeah!
Watch out!
Oh, it's coming in hot. Look out! Yeah!
Let's finish with Neo and Trinity.